Alright, in this video we're going to be looking at coding projectile motion with air resistance. So, let me go over here to my notes and let's just talk a little bit about an object that's moving through a fluid. We'll be experiencing a drag force. You can see here that I've shown it as F air, and this is a little guy that's dropping out of a helicopter. So initially, if you look at it, he's just accelerating with an acceleration of negative 9.8 meters per second squared, and there's no air resistance. But as he starts falling through the air, we get this upward force of drag, all right, and our acceleration suddenly changes. Maybe it's, I don't know, negative 5 meters per second squared. Eventually, at some point, the air resistance force could be equal to the weight force going downwards, and then your acceleration here is now 0. And this is what we would call a terminal velocity. Okay, so what we want to do in our coding here is to look at not just having something accelerate only due to gravity, but we also want to include now air resistance into the problem. All right. If the object is rather small and going relatively slow, then the air resistance is directly proportional to the speed. This is if it's slow and small. But if the object is really large, like say the size of an airplane or even a skydiver, maybe even a baseball, then we could say that the velocity squared is proportional to the force. Now this is if it's faster and also larger. So we're going to actually really be using this equation. All right. The equation for air resistance depends on a number of qualities, and we talked about that a little bit in class. Technically, the equation is 1/2 times the drag coefficient, which is C here, the density of the fluid here, which is rho, the cross-sectional area of the object, and then lastly, the speed of the object squared. So this is technically the equation we're going to be using, but I am going to simplify it a little bit in our coding, and we're going to be simplifying it to just simply writing C times V squared, and also a direction to it, which would be negative. If we're considering positive, go downwards. So now on to the force analysis. So as the skydiver jumps out of the airplane, we can see that the acceleration initially is negative 9.8, and then it starts to change and get smaller in magnitude as he starts to fall because the air resistance force gets bigger. So we need to develop a relationship for acceleration. And so if you recall Newton's second law, the sum of the forces equals mass times acceleration. So the net acceleration, I guess you could call it, is equal to the net force divided by the mass of the skydiver. So this net force, okay, is a result of two forces. We've got the force of gravity, and we have the air resistance force. So I'm going to make the air resistance force be negative. I'm going to assume that positive is going to be going downwards, all right? So that our acceleration values, instead of being, say, negative here, they're just going to be positive because they're just simply going to consider positive to be down. Okay, so our net force we're going to be calculating by using Fg equals minus the air resistance force. We're going to calculate our acceleration by taking that net force and dividing it by the mass. And then we're going to need to be updating the velocity and updating the position as the acceleration changes over time. So let me go to the instruction sheet that I shared with you, which is here. And so our goal of this activity is that we want to model the object's motion and include air resistance force. And so we're going to be using a simplified model, which is this equation right here. The air resistance force is given by negative C, the drag coefficient, times the magnitude of the velocity squared, and multiplied by this little factor called the unit vector. We're going to normalize the velocity. It might be a little bit weird because we haven't really talked about unit vectors. So maybe I'll just spend a tiny bit of time talking about how we can normalize a vector. You see, going back to here, when this object is flying through the air, you'll see that the air resistance force is going to be in the opposite direction of the velocity. So if he's moving downwards, then the air resistance force is going to be upwards. So if I have like a baseball that is flying through the air, then we're going to see that the the force of air resistance will be in the opposite direction. If the velocity is this direction, tangent to this dashed line here, we got force of gravity going down, and our air resistance force is going to be in the 180 degrees opposite direction of the velocity. So how do we do that, right? We have to use something called a unit vector encoding. Okay, so let me just explain that a little bit. So what is normalizing a vector? So imagine I have a vector that is, let's say, 10 units long and at some angle theta, right? What we want to do is we want to take that vector, let's call that vector A, and we want to normalize it. So we want to basically keep the angle the same, but we want that magnitude to be 1. So let's say if I had a vector that had, let's say A here, it went, say, 3 units to the right and 4 units up, we could see that the hypotenuse of this triangle is 5. So if you thought of this vector in terms of components, you could say it's 3 along the x, 4 along the y, and 0. So if we want the normalized version or the unit vector of that, all right, we'll call that A hat. It's going to be basically 3 over 5, 4 over 5, and then 0 because 0 divided by that. So what you're seeing, hopefully, is that if you were to have a vector that's 3 over 5 and say 4 over 5, then the hypotenuse of that triangle is going to be 1. You could work it out. But we're going to still maintain that same angle. We're just now going to have a vector that has a magnitude along the hypotenuse. It's just going to be 1. And so that's what we call normalizing a vector. So in this case, we're going to be using a velocity vector. And our velocity vector, let's say, is 3, 4, 0. And v hat is basically what we would call the unit vector of v. And so that would be really taking vector v, and then we're going to divide it by the magnitude of vector v. Okay, encoding, we're going to call that v hat basically v, which is a vector, and we're going to divide it by mag v. Okay, why are we doing this? Because we are going to be taking our air resistance force right in here, all right, our expression that we have, and we need to have that air resistance force point in the same direction of v, but we need to multiply by -1, so it points actually not in the same direction v, but in the opposite direction, so 180 degrees. Okay, so maybe a little bit confusing, but I'll tell you that in the coding I kind of tell you what to do and I show you that. So what you're going to need to do now here is take a look, maybe pause the program I suppose, and start looking through this code and see what you can do to do it. Alright, so maybe open up a program in GlowScript. Alright, so here's GlowScript. I've just created a program here. And I'm going to, and I kind of give you in this instructions kind of things that you should do. So first thing I want you to do here is I would like you to create a ball and the ground. So just simply copy this code over here to GlowScript. Okay, paste that right in here. Hopefully you can see that. Maybe I'll make this a little bigger so you can see it. All right, the next thing is that we are just simply creating the ball and the ground. Okay, there you go. The ball obviously is not moving yet. And so now we're going to have some initial parameters. And again, I also kind of tell you what I want you to do. Maybe I'll copy all this bit of code in here, but I need to actually make it more into code here. But I don't tell you exactly what to do. So the mass is 0.3. I'm just going to simply call it m. Okay, you can kind of add in comments as you wish and say this is the mass. Whoops. Interesting. So this is the mass. Whoops, didn't do that again. Here we go. Mass ball. All right, then let's fix some things up here. Velocity. This is not written quite correctly. So this is v, and we need to tell that it's a vector. We're going to use like just normal curved lines, and this is going to be in meters per second. So just maybe put a comment in here. We're doing in meters per second. Remember that it is a vector. Okay, and v hat, we're using that. The same thing we're going to do with gravity. We're going to call that a vector. Okay. And then we have also the force of gravity, which is simply multiplying the mass by g. Now turning that into it. We have the drag coefficient. All right. We have the time variable. All right. And we set at 0. All right. And we have the increment of time. Okay. That is going to be in seconds as well. So those are our initial parameters that we're setting in here. And so now we need to set up the loop. So again, in the code, I kind of tell you, I would like to basically keep moving the ball until it reaches back into the ground. So I'm going to highlight this bit. That is the beginning of our code. So our loop. So paste that in, then press enter, and now you're into your block code. So, and once again, I've given you some of the instructions. These 3 lines are going to be basically determining the net force. So you can just copy those right in there. Whoops, where is it? Right there. I'm going to paste that in. But remember that you need to have everything indented. Okay? So this is basically calculating the unit vector of the velocity. This is calculating the air resistance force and then making sure that it's rotated in the right direction. So that's why there's a negative in there. And then this is our net force, which is the weight plus the air resistance. And you notice I didn't put minus in there because then minus is already over here. Okay, and what else? Well, we need to update the acceleration, right? So we'll update the acceleration by using A equals F net divided by mass, right? That's how we calculate acceleration using Newton's second law. Next thing we need to do is we need to update the velocity. So we're going to be using the Euler-Kromer method. So we're just simply going to take V, the new velocity will be the old velocity plus A times dt. Remember, A times dt is a chunk of area under that acceleration time graph, which gives you a change in velocity. Okay, and then once we do that, we are then going to update the position. And here I give you, again, the code that you have to write. It's ball.pos equals ball.pos plus V times dt. Okay, and then we want to increment time. Okay, now one thing that you may have noticed is if you run it, you may notice that it goes, oh, let's see, oh, I have some errors. Oh, yeah, brackets. All right, let me just fix that up here. So you can see that this should have been a nice circular bracket there. Let's run it. But there is an error. It ran so quickly I didn't see it happen because I did not put something to slow my animation down. So I need to slow my animation down so I can see it. And so we have rate 100. And what is going on? What am I missing? Maybe you take a look at the code for a moment and see what I'm missing. Actually, I think it was working properly. I just have to run it and just wait for it to load up. And there it is, my projectile motion. Now you can play around with the coefficient here, change that to say 0.5 and see how that affects it. If you had more drag, you can see it doesn't go as high. You may want to add in here with our ball a make underscore trail equals true. That way when we are running the program, you can see the path. You can see that it's not following a parabolic path. Okay, there's air resistance. And so this video is already getting a bit long, but I'm going to leave it up to you to actually add graphs for vertical position and horizontal position over time, the velocity over time as well, x and y. And also I just tried changing the coefficient and see how that changes. And then now, really tricky is, what angle do you think you would have to fire this off at so that it would go to the maximum distance for a certain particular coefficient, drag coefficient. So that I'll leave it for you guys to kind of play around with that. You may want to kind of use a nested loop, like some kind of 1 to 100 trials and just keep incrementing the angle. All right, but I'll leave it for you to figure out. Hopefully this is enough at least to get you started if you didn't get the first part of it. Okay, that's it for the video.